Hello, welcome. Today I'm fulfilling a promise I made a few weeks ago, and we're going to learn all about how I did my procedural island generation. So here's what it looks like. I'm working on a little fishing game, and for that game, I wanted kind of this roguelite random generation of islands that you can travel across to each island and go fishing at each one. And I had never done procedural generation like this before, so proceed at your own risk. I'm still learning myself, but for what it's worth, it's working pretty well for me, and I like how it looks so far. It's a little bit plain because I haven't added like a little bit more variety and like clutter, trees, rocks, things like that. But I'm pretty happy with how it's generating the land and the water itself. So I'm going to cover the entire process from creating the 3D assets to writing the code to rendering all of the objects that you see here. I'm using Godot for this, but if you are familiar enough with your engine of choice, you should be able to follow this tutorial still and adapt it to your engine. And I'm gonna remember to make the code bigger so you can actually see what I'm doing here. So before we get into the bulk of the tutorial, as I mentioned in the dev vlog where I talked about doing this work, I had not done procedural land generation before, but I was aware of an algorithm called wave function collapse that's been used for things like this. I've watched a few videos about it before, and so I used that as my starting point. I didn't really look at other options, but I'm sure there are some. With programming, there's always a lot of ways to solve the same problems. So this may not be the right solution for you, but it was the right one for me. I also made some mistakes as I initially programmed this. I had to go back and forth a little bit, solve some problems. So in this tutorial, I'm going to skip the problems and go right to the final solution. But if you want to know more about what I did and what I ran into, you can watch the dev vlog where I talked about all this. So the way that wave function collapse works is that you start with a space that you want to fill in a set of options that you can fill that space with. And in this case, we have this grid that we want to fill with land or water tiles, and those options all have constraints. So like for example, this little corner piece here can only be connected if pieces on this side and this side look the right way, otherwise it won't fit, it won't work. So there's constraints on all of these where the pieces can only be placed next to certain other pieces. So the algorithm goes through a cycle of getting all the compatible options of a certain slot, selecting one, continuing repeating that until either the space is full or there are no viable options left, in which case the procedural generation is like unsolvable. You'll have to either find a solution for that or start over. And during that loop, one very important step is to prioritize the options or the slots with the fewest options, because otherwise, if you do it completely randomly like I did initially, you'll end up with spaces where nothing fits, and then you'll have a broken generation. You'll have to redo it, you'll have to solve the problem. It still happens very occasionally because my tile set is not complete, and I'll talk more about why I chose to do that later. It's something to watch out for, and prioritizing the slots with the fewest options really helps. And all of the tutorials I watch refer to that value, the tiles with the fewest options, as like prioritizing the lowest entropy or the highest entropy. I'm not totally sure. Like I said, I'm still learning. So before I wrote any code, I made the pieces for this system, and I did this in 3D in Blender, and you can actually use very similar code for a 2D system if you would prefer to do that. The generation code is going to be almost identical, and then it's just the rendering code and your scenes that you set up that are going to be different. But I'm going to talk about 3D, which is a little bit more fiddly because it is in that third dimension, and also it has to deal with things like lighting and normals and trying to get things to match up. So I'm going to go over this, but if you prefer, you can just use 2D tiles as your tiles, and it's a very similar process. So the first question to answer about your procedurally generated pieces is actually just to decide what kind of options that you want to have in terms of like compatibility between the pieces. And the very simplest way to do this, and the way you can guarantee that you'll have a solvable generation no matter what, is to do something like this, where I'll pull these out here. So these pieces This was a failed attempt actually because I did not like how it looked. But if you look at these pieces, every single one has all water or all land on one side of the 4 sides. So with this, you can make 16 different options, and no matter what you do in your generation, there will always be something that fits because you're covering every case. As you can see, at least the way that I did this, it's like very unnatural looking. It's not very smooth, and there's probably ways to do this that look better than what I did, but this is what I came up with, and I did not like it at all. So I didn't use that method. I used a different method. The method that I used is basically imagining, you can see on the grid here, imagine that each tile is split into a 2x2 grid. So we have 1, 2, 3, 4. Each of these can be land or water. So for a more interesting one, we have one like this, land, water, and we also have like some like this. So I have this whole set of pieces here, and they are not complete, so you can get into situations. For example, if you have land on this side and water right here, this piece cannot be filled in because I don't have any pieces that are land, water within one corner. So that's fine. It's really fine. What'll happen, like I mentioned, is that some iterations will just not be solvable, but for the most part, as we can see if I just run Godot again, the algorithm is able to fill these in most of the time. Let's see if we can get a failed one. It actually doesn't. Oh, there we go. Wow. How convenient for me that this decided to fail the exact time that I wanted it to fail. So in this one, obviously we can't use this. It doesn't form a cohesive island. But now if we're lucky, this next one will work. See? So it's just something you have to keep in mind, a sort of trade-off. What I could do is I could go in, I could make more tiles for all those cases that are unsolvable currently, but for now, this works well enough. And sometimes this is the decision you have to make for code. Does it work well enough? Is it worth the effort you're going to put in to completely make every tile that fits? And I personally think the answer is no, especially as you create more complicated systems. Like for example, I only have land and water right now, but what if I wanted a tile that transitions into a mountain with a different shape and a different edge that connects? That adds another sort of dimension to the number of tiles I need. And I may not want to do an additional like 32 or whatever tile options for that biome set. So this first step is just deciding how you want the tiles to look and how many tiles you're really gonna need. And then once you know what you want, you have to actually make the tiles. So what I did was I started with this all land tile. It's one tile off the ground, so each of the tiles are either going to be down at the bottom for water or up here for land. And actually, I'll mention now, one thing I would like to do is go through and actually remove the water tile because I'm doing water with the shader. I added the shader a little bit after I started working on the land tiles, but because this is like this, it limits how deep the water can be. So I am actually going to take that out. So that's something that you can think about if you're also doing a land water thing, is that you may not even need mesh down here. But it's in for now just because I haven't gotten around to moving it yet. But basically every single edge lines up perfectly with this square. So no matter what it is, all the edges line up perfectly with this square. And you can just do, like you can grab the vertices and you can set the values here. So these are on this side, so x needs to be 1. And then another thing to look at this dimension, all the ones that connect to another edge that are at the top should be at position 1 for z, up and down. And then all the ones for the water, I can just grab these here. All these should be at 0. It says -0, which is not a thing, but But that's that. And you'll also notice the next thing that you need to worry about. And so if you have all the positions of the vertices lined up just like this, you may still encounter some weird like seams between the things. And I was seeing this and I wasn't really sure at first why it was happening. And then I realized it's because of the normals. Normals are basically a value that's stored in each vertex that says the direction that is perpendicular to that vertex. You can see all these ones on top point up, these ones on the side sort of point out to the side. And what was happening was that if I had a lot of variation, I'll just move this for a second to demonstrate if we can see. If there's a lot of variation between the next vertex here, you can see the normal shifts around. So if the normal is pointing like this, for example, when it's shaded, it creates a sort of shadow. And so part of this is making sure I have normals on the sides here that are roughly straight out so that the shading doesn't look weird when it gets in there. And there are ways to actually adjust the normals, I believe. I don't typically do that, so I didn't know how to do that. But what I just did was make sure that the very first vertex was basically right along the axis line that I was lining it up with. And in some cases, let me see if I could find a good example. Yeah, like this one, I did actually add another edge here, just so I could have this sort of curve around a little bit without having to worry about messing up that edge normal. And then as a final step, I want to make sure the position of each piece that I'm exporting is in a very predictable spot. So you can see if I enable these, they are all in the very middle and they are all the same size in every direction, so that when I instantiate these models in Godot, I know exactly where to put them to place them next to each other. So for example, if I take this, I offset it by 2, you can see it exactly matches it up right there. I would highly recommend taking some of these, moving them around, because I just didn't do this. And so the first export I did, I had all these problems I had to fix that I would have definitely seen if I had just moved these around a little bit and tested it out before exporting. I just kind of thought it would work, you know, and it didn't. And so then I had to do a little bit of back and forth. So save yourself some time, test it early, make sure it works, and don't put a bunch of time and effort into making the models until you're sure that you're actually doing them the right way. Another thing I would highly recommend is giving these a naming scheme that is very clear to you so that you know exactly which piece is which. So for my naming scheme, I just have 4 letters, and I'm starting at the top left. 1, 2, 3, 4. That's what the name of each piece is. So L L W L L L W W. So when I import these, I know exactly which mesh is which, and I don't get confused later when I'm actually hooking all this up to the code. So I've talked about how I export models from Blender. I do them as a GLTF 2.0. Once we have everything exported, so in here I've exported all of these. I've got them all here. I made a folder called land models, and I've exported them. Oops, they look kind of wonky in this preview, but they all look fine once you get them in the game. And once you have all the pieces, you are going to need some way to define what they are so that your code can figure out what pieces you have and how they're compatible with other pieces. And this is where I learned about Godot resources, which are similar to Unity's scriptable objects in the sense that you create them at design time, you put data into them, and then they can be loaded and used by the game at runtime. I also found out that resources don't work quite as smoothly in C# as in GDScript. They don't come up in the search when you're creating a resource. So what you do here, and I'll show you, I have the definition of land resource in this script folder, and then the resources themselves look like this, where I've had to set this as a regular resource and then drag the script right into here. But let's go look at what the resource definition looks like. All right, so when you define a resource in C#, you do it like this: public partial class, the name of your resource, and then it inherits from resource. In here, first I've got two enums related to this resource: the edge type, which is currently either water, land, or none, and then the edge position, which is top, right, bottom, or left. And I did have to do a little bit of a weirdness because of I check the edges, but my individual pieces are not just all the same along one edge. So I've had to make the code a little bit interesting to account for this, but in the end I think it worked out. So we'll talk about that. So I just have two properties exposed to the inspector. I have an array of the edge types, and these go in the same direction as I define the names. So top left, clockwise, I just define each of the edges. And then I have a path to the model. So this is going to be a string, and it's going to be a path to the model that it should load if this is actually drawn in the scene. And then I have just one function in here. There's a string override. You don't need that. That's what I use for testing. But I have this function called isCompatibleEdge. It's a Boolean. But basically what this does is it gets the position we want to check, and then the first and second types of the edge of that incoming tile that we want to check against. First, we make sure that we have the number of edges that it should have, that nothing has gone wrong here. And then if it's the bottom edge, we check edges 3 and 2. If it's the left edge, we check edges 0 and 3. Top edge 0 and 1. And then right edge is 1 and 2. So this is all very much based on my system. If you have a different system, you're going to need to rewrite this so that when someone calls this function and they pass in whatever parameters you need, it will check, is this thing that I'm trying to put it next to valid? So whatever that looks like for you, if you just have the 1, 2, 3, 4, the entire edge is the same, this will be a little bit simpler. Because all you'll really need to do is check it against, for example, if it's the right edge, you check it against the left edge of the adjoining piece, things like that. So that's what this function does. So after making this land resource type, the way that you add these in Godot is you do create resource, and then if you're using GD script, if I were to type land resource in here, it would show up in this list, but because the C# resources don't properly get added into the system here, I have to create a normal resource, give it a name, just test resource. So I'm going to delete this one later. And then you'll see the script here is empty. So you can go down, you can get your script that you made, and then it will work. So that's an extra little step to do for C#. A little annoying. I don't know. I keep running into tiny things like this that make me think maybe I should switch over to GD script, but I haven't been convinced yet. But I made a resource for each of these, filled in this array with the types of the edges, and then the path to the model. So the models I made basically just by creating a new scene from each model. And then I made a couple of changes in here. I added a collider, and that's kind of it, actually. Some of them have like places where water can be added, or a fishing node rather. But for the most part, these scenes are basically just the mesh, some colliders, and not much else. And this is another thing that will depend on your implementation. Like what you're gonna need in this scene will be different based on what you're doing with it. If you literally just want to render it, you don't need colliders, you don't need anything. You could just load the models directly. So now that we have our pieces, we can get into the generation script. So at the top of this script, I just have a few properties that are revealed to the inspector. I have a set of all of our tiles. So this is an array of land resources. And when I fill this in the scene, I just put in every different kind of tile that I have. And then I have a land tile and a water tile, and this is used specifically because I want one land tile in the middle. I might eventually put it near the side actually, but for now it's in the middle. And then I want water all around the edges. And this is just a way of constraining it to be an island, you know, and the island is surrounded by water. And then I want to make sure I have at least one land tile to put the player on. And so that's what this is for. Don't worry about anything related to fishing nodes because it just makes it a little bit more complex and it's not really relevant to other games. But I've got a reference to the fishing node object in here. And then I've got the radius of the map. So it is a grid, it's not a circle, but I had originally done things a little bit differently, so I've called it the radius. But I have the radius or the size of the grid, and then I also just have another fishing node property here. And then I have a two-dimensional array called current slots, and this is what's going to hold all of our slots that we're going to fill, and then eventually it's going to also hold the tiles that they're filled with. And I've just initialized to be the size based on the map radius. Got another fishing node property here, and then I also have current lowest entropy. This is used within the loop to keep track of which tiles have the fewest number of options. And I have a lot of private functions in here that we'll talk about later, but first we're going to get to the public function called generate island. This is what does the main loop. And the first thing we do is create a random number generator. We use randomness in a couple places in this algorithm, and so I just want to have that ready. Another fishing node thing. And then before we do anything else, we need to generate all the empty slots and also put in those default ones that I talked about before. So that's right here. And basically we just loop through the whole grid. For each slot, we add a new tile slot. We set the coordinates. We set the entropy to 0 for now. Initialize the list of compatible tiles, and then the selected tile is where we're going to store what we've picked to put in this slot, and for now it is null. And then down here all we're doing is adding that land tile into the center of the map, and then we go through the top row and the bottom row, we add in water tiles, and then we do the left and right rows that connect it, we add the water tiles. So this just creates a ring of water tiles around the outside edge of the map. Before we get into the loop, I do have a loop counter. This is used for cases where we can't solve it to stop it from going forever. And generally I just recommend, if you're making a loop and you're a little bit uncertain, maybe it's something you've never done before, you're not sure how you're going to terminate the loop, you can always add something like this that will just get out of there when you've run it a certain number of times. There's no shame in that, especially as you're figuring things out. So I do use a do while loop here because I felt like that fit the situation the best. And the first block here just goes through and it updates all the values based on the tiles in the map. So we set current lowest entropy to a very high value so that we know when we encounter even a relatively high value, it's going to be lower than that we can set. We loop through all of the tiles in the map, and we don't want to worry about slots that already have a tile selected because those are not important for our algorithm. So if we've already got a selected tile in here, we're just going to skip past it. Otherwise, we're going to get all compatible tiles for coordinate. And let's look at this right now. Okay, so this one also is going to be a little bit different depending on what you want yours to do. But this is what mine does. So it will return a list of resources that all fit within this coordinate based on what's already in the map. So what I do here is I look at the tile above it, the tile to the right, the tile to the bottom, and the tile to the left. So these blocks of code are just me getting the relevant tile. If there is a selected tile, we want to get the edge types. And we want to check all 4 edges, make sure it fits in there from every side. So we've got that for the right tile, we've got that for the bottom tile and the left tile. And then once we have what all of those edge types are, and they can also be none if there's not a tile there, so we take that into account as well. Basically, we loop through every piece in our set of options here, and we check if this edge is compatible. We pass in those edge values that we grabbed, and we also check that there actually is a tile here. And if it is not compatible, we set is valid to false. Otherwise, we just keep falling through to the next check. If we get through top, right, bottom, left, and everything is still valid, then we add it to the list. And I want to talk for a second about what you might have here as different constraints. So, I'm only constraining it by the types of tiles. You might have something else. For example, if you have a map where you can only have 3 of a certain tile, what you'll want to do when you're looking for tiles that are compatible is if you've met that limit already, that tile is not compatible. So you'll want to have that somewhere, maybe it's in a different function, where you actually check that constraint, and if it's not compatible, you remove it from the set. You might also have a constraint where a tile can only be placed if another tile is already on the map, something like that. And so that's another thing. You'll want to add a check for that. And if that situation doesn't exist, that tile is not compatible. So you can really use your imagination here and create a lot of very interesting constraints, or you can keep it simple like I did. It's up to you. So if we go back to our thing here, we get all the compatible tiles for that coordinate, and then we set the entropy, which is just going to be, for me, I'm not sure if I'm using this word exactly right, but for me, I'm using the count of compatible tiles. And so we want to prioritize the tiles with the fewest compatible options so that we're filling those first, and we have a lot of other options for all the remaining tiles. And, hopefully. As we're looping, we update what the lowest entropy is. So if this new value is lower than the current lowest, we update that. That's just getting the minimum. And then once we've gone through this loop, all of the open slots should have an updated list of compatible tiles and their entropy value. So the next thing we do is get next open tile. So this is another function here. And we take in our random number generator because we use a little bit of randomness in here. We can't fill in a tile if there's no options for it. I do update the entropy. If it's 0, I update it to 1. What I need to be doing here, I think, is actually right here I should be triggering like a retry, abort the current generation, retry it because we've encountered a situation where we've run out of options. So I need to do this a little bit differently, but that's kind of what the thought was there. And then we want to get all the slots that have the fewest number of options, and we want to pick one of those at random. So I've got a list here, lowest list. I loop through the entire grid. If the selected tile has the lowest entropy, we add it to the list. I could do this a little bit more cleanly, I think, with like a link query, but I just didn't do that. But that's something you can do if you want to make it a little bit more tidy. And then if we didn't find any tiles, any slots with that lowest entropy, we've encountered another problem, so we're returning null there. Otherwise, we return an option from that list. We use the random generator. Rand I range is an integer, so we go from 0 to the highest index of the list, and we return that value. So there we are. We've got our next open slot that we wanna fill in. If this return null, if we have no more open slots that we can fill, we do break out of this loop, which will jump us down here. This is how we get out of the loop when we're done generating it, and then it also gets us out if we've gotten into a situation where we can't actually complete the island. So in theory, we should never actually hit the loop break, but either way, I have it in there just for a little safety net. So once I know which slot I'm picking from, getting the tile we want to fill in there is really easy. We do almost exactly the same thing. We have all the compatible tiles already because we got them up here and we filled them in. So I'm just using that random number generator again, rand I range, to get a random option from the array. So we grab that and then we fill it in as the selected tile. So the next loop, when this goes through, this selected tile is not going to be null, so it's going to skip over all this, and every time we run the function, we're going to have fewer and fewer tiles to worry about, and eventually we are going to have a complete grid that is filled with tiles. And once we get to that point, we will break out here and we will render our tiles. So currently everything you're seeing here is just in code. There's nothing on screen when all this is happening. It should happen very quickly. You could also add like a little loading screen if your algorithm gets a little bit more complicated, it takes a long time. But for me, all of this happens and then we render the tiles out. And rendering the tiles is actually very easy. The tricky part was all this stuff that we did in figuring out how to sort of solve this puzzle, get everything in the right spot so that it matches the slots that are next to it. And so now once we have this, it's very simple to actually render this out. So we've just looped through all of our tile slots and current slots. And actually I could be using this in all of these other loops. I just didn't realize that this would work until I got to this point because we are saving the coordinates in the objects. Anyway, that's irrelevant. For each of the tiles, we make sure that we have actually selected a tile for it. In the case where it doesn't solve correctly, you saw it does still try to render out the ones that did work, but it skips over all the ones that don't actually have a model to load. And this is where it gets into very engine specific stuff. I'll probably clean this up at some point and move the rendering into a different files just so it's a little bit more separate. But here we are using gd.load to load our scene. I'm not sure what this looks like if you're using 2D tiles, if it's a different process to just load an image. But I pass in here my model path. So this is the path to the whole model ready to go with all the colliders and stuff in it. And then from that we instantiate it. It's a node 3D. So this whole thing will load that tile into this variable, and then we set the position, and I'm offsetting this from the radius because I want the position of the tiles to start at 0, 0, and so that's all I'm doing here. And then we multiply it by 2 because I know that each model is 2 units wide, so they need to be offset by the coordinate and then the width and the height of what the model is so that the next one lines up perfectly right next to it. And I should probably also pull this out to like a variable. This is kind of a magic number, which is generally you should avoid magic numbers or numbers that are in your code that have a meaning, but the meaning is not clear. So if I instead pulled this out into a variable that's like tile width or something like that, that would be the better way to do this. So I'll probably clean that up after I'm done filming this video. And so once we have that tile, we've set the position. This is resource node stuff, so this is not important. But basically what I'm doing here is getting resource slots from this node and adding them to a list so I can fill them in later. But this is all irrelevant to generating the stuff. That's for something else. So all we do is these 3 lines. So we load it up, we instantiate it, we set its position, and then we add it as a child to the hierarchy, and then it'll show up, and that's it. All this other stuff is related to adding the resource nodes, so this is totally separate, not relevant here. So really it's just this. Once you have that, you've got everything you need to generate this island. And then I do also have just a little scene that I'm doing all of this in. So let's just look at, and there's really not a lot here. I've just got like a reference to the generator object. I generate the island, and then I spawn the player. Since all the code is in here, there's not really a whole lot to do in the calling code. So it pretty much works just as it is. So I've got that object here, got the island generation script. And then I just pass that reference in to the scene object and we're good to go. And that's the entire process. Whoops, our first run at the end here did not work, so we'll try again. And like I said, I need to add, 2 in a row, that's bad luck. Okay, whew, that was weird. Like I said, I do need to add code that will automatically retry at least probably twice if I get a failed generation because of how I'm doing my tiles. But this is it. This is working. And this is really the beginning of a system that can be a lot more complex if you want it to be. As you've seen, I've already started adding a little bit of complexity with these fishing nodes. It spawns 5 of them in sort of random water positions in the island. You can also do things like generate trees, ground clutter, creating different biomes that transition into one another, procedurally placing points of interest, which is kind of what I've done here. It's a very flexible system, and you can really build up off of this into something a lot more complicated that's going to make your game very cool. So hopefully we'll see some more interest here taking shape as I start to add pieces and add some visual flair to this island system. But that's all I have for today. Don't forget to like this video and subscribe if you'd like to do that, because I'll be back soon with another video, and I hope to see you there. Goodbye!